I made this graph plotter in Python and Qt. So today we are going to talk about some optimization method behind this plotter. Okay, so first thing first is like whenever you run some kind of a 2D or 3D engine, you always have this zoom in and out, which actually makes objects smaller or larger. But for this kind of scenario where we actually want to draw functions, we don't want that. We always have to need some kind of a consistent line thickness and labels and grid lines and everything, so user can actually see all the time what he actually wants to render. So that's actually all ran by this function from the view pixel to world, which basically defines thickness in a pixel values and just map it to the world. And that's used through all this example for the grid lines, subgrid lines, axis, labels, everywhere basically. So you just define thickness in a pixel values and map it during the rendering to the world values. That's not kind of optimization method, but something under the hood, why it actually looks how it looks. So first optimization method is this debug margin, which is kind of like just a frustum calling. And this is actually saying like we are rendering 10 pixels in each direction outside of our view box. So if I put something like a 300 and rerun it, you can actually see we are now rendering much smaller part. And that's kind of like for the debug for now, just so we can actually see how much of it we are actually rendering. Because in most of the cases, like domain can go from like minus infinite to the infinite, so we cannot draw like a infinite amount of lines. So we have to actually render only on the parts that user can actually see. How we actually do it, it's pretty simple. I'll just return it to 10. Whenever we do something, let's say build grid, and we have this debug margin, we just actually squeeze our rectangle or a bounding box to where we actually want to render by actually adding to the minimum x and y values and subtracting from the maximum values. So that's pretty neat optimization method. Second thing is like adaptive sampling, which means we don't have to use every pixel for the domain because no one can actually see that much of a detail. So currently it's 6, but we can actually see it visually if I just like, let's say put 16. Then you can actually see that we actually don't render on every single pixel, and then this curvature just represented of like a straight lines. So I found like the 6 is the best value, so it kind of saves us a lot of this computation power, but we still get enough detail. And this max function segments is basically like a maximum limitation for this exactly the same thing. So like this actually defines you're just going to use every 6 pixel, but this actually is on the top, like limiting it, like we don't want to have more than 1200 segments. So like it's again limitation for the user. And the last one is this curvature epsilon. Basically what it means is like if we draw something here, you can actually see like on this modified scene wave, we don't actually need the same amount of points in the domain where we have like a curvature or where we have like linear lines. Basically it's not linear lines, but there are not as much of the curvature there. So how we do that is like we compute the second derivative and basically get the slope of that function. And if that slope is in this case less than 2% of the pixel value, that means we kind of don't really have much of a curvature there. So we'll just remove that domain point and use the previous and the next one to draw the line, because not much has been changed there. That can go on and on. So like if it's just a linear function, we'll just remove most of the points there. So like if I just put something massive here, it's gonna be pretty weird. You will see a lot of artifacts. Yeah, so this is just now a line, but like, yeah, I just put too big value. It's like a 50 in this case. So that's kind of most of the optimization method to make it work. I hope you found it useful, and yeah, thanks for watching.